We're moving on to the second lecture of the social cost of carbon and integrated assessment models. You should watch the first lecture on this before watching these. Today we'll be talking about the basics of the DICE model. We previously defined the social cost of carbon and outlined integrated assessment models. Today we're moving on to the basics of the DICE model. What is the DICE model? It's an integrated assessment model, and it stands for Dynamic Integrated Model of Climate and the Economy. It was built by William Nordhaus at Yale, who is a Nobel Prize winner for this his work on this topic. He's written a lot of books and a lot of articles on it. I encourage you to look him up and look at his articles. So today we'll outline the most important and simplified equations determining production, investment, and emissions in the DICE model, and equations describing how capital, greenhouse gas concentrations, temperatures evolve over time. And then finally, an economic welfare function is maximized adhering to the above equations. Here is the flow chart on an integrated assessment model again. We'll start with population, technology, production, and consumption, which leads into emissions, atmospheric concentrations, radiative forcing, temperature rise, and global climate change that are translated into damages or direct impacts. Then that's all fed back into the next period, production and consumption. Production. Production in period T output is given by the following equation, YT, which is the composite good or GDP. It's a function of 1 minus lambda, where lambda is the abatement costs, over damages, DT, in period T. So all the T subscripts are the time periods, multiplied by AT, which is the technological progress in the current period. Technological progress is basically how we turn capital and labor into GDP. KT is going to be capital in period T, and LT is labor in period T. The exponents gamma and 1 minus gamma are the elasticity of substitution between capital and labor, how we convert or how we can substitute labor and capital to produce the same amount of GDP. So it's kind of like using machines to do the jobs that humans have been doing. How good or what's our limit of doing that? Some things cannot be done by machines. Some things cannot be done by humans. So the things you should ask yourself is, how are each of these affecting GDP? How does capital affect GDP? Capital and labor are being translated into GDP via AT, the technological progress parameter. And then abatement costs are actually coming in as a negative here. They're decreasing GDP. Now, some people argue that this is maybe not how we should be modeling this. Some people argue that abatement cost should actually be a positive, because we're investing in abatement. Maybe we are investing in battery storage for electricity. We're investing in solar and wind, and that should be considered a positive to GDP. We could change this in the Excel model if we wanted to, but for right now, its model is a negative. Abatement is reducing our GDP. So you should pause this and ask yourself the question, how do emissions affect the production process? Where do emissions enter this equation? The answer to this, if you paused it and thought about it, here's my answer to this. Well, everywhere. Damages, or emissions are a key component of damages. As emissions go up, damages go up, causing this function to decrease. DT is in the denominator, so as DT goes up, YT goes down. So GDP is going to go down as emissions go up from damages, or damages go up from emissions increases. Abatement costs, an increase in abatement causes output to go down. Again, this might not be the right way to model this, but that's how it's done right now. At the same time, increasing abatement costs decreases damages, so there's an implied trade-off between more damages and or fewer damages and more abatement. Emissions also affect capital and labor, as well as through population and capital stock evolution. We will define how KT evolves. So note that KT plus 1, or capital in the next period, T plus 1, is a function of GDP in the current period. So if GDP in the current period goes down, then capital in the next period is going to go down, which causes GDP in the next period to go down. How do we get the values in the DICE model? Labor is taken as exogenous. It's an estimate taken from population models. So labor is basically just the global population. And it's not, exogenous means it's not affected by things happening in the model. Endogenous would be something that is affected by things happening in the model, like capital in the next bullet point. Labor is exogenous. Maybe we should adjust that given what we're learning about the current pandemic. Climate change is forecasted to increase the number of tropical diseases, which would obviously decrease the stock of labor, the population, if tropical diseases end up killing people. So maybe labor should not be exogenous. Capital is calculated as part of the model. It's endogenous, but the initial endowment, the initial amount of capital that we have is exogenous. And you can adjust this in your Excel model. The parameter gamma is estimated. This is the elasticity of substitution again. It's estimated to be 0.3. The technological progress, AT, is exogenous. It's how we're translating capital and labor into GDP. Damage is approximated as a quadratic function of temperature. So dt is this equation here. A0 is our intercept for damages, plus A1 is the coefficient on linear temperature, temperature in period T, plus A2 times temperature squared, plus a function of sea level rise, plus a function of CO2 fertilization. The cost of emissions reduction is estimated as a function of lambda, the emissions control rate, and of the emissions control rate, which is basically any policy we're imposing in the model. So lambda is a function of the policies that we impose. A more stringent policy is going to increase lambda. Questions to ask yourself. Pause this video. What assumptions are made and how might they affect the model output? We've already talked about labor being exogenous. Maybe that should be endogenous. Technological progress being exogenous is also an assumption. The shape of the damage function is an assumption. Should the shape be quadratic as it is, or should it be exponential? Should the damages be exponential as the CO2 rate goes up? Or maybe we should have a step function where we are accounting for tipping points, and once we hit a certain level of damages, then, or a certain temperature, then damages are essentially infinite. We can't go back. Another question is, what shape do you think the abatement cost curve is? Remember, our marginal abatement costs are downward sloping. If the x-axis is emissions, if the abatement cost curve is downward sloping, should it be that the first unit of emissions we abate is really cheap and the last unit is a little more expensive, or is the last unit very expensive or even infinitely expensive? So getting rid of CO2 from our production process completely, is that impossible? In other words, infinitely expensive to do, or is there a price on that? And what shape is that marginal abatement cost curve? A couple points of interest on production. The population growth rates are logistic in this model, so they reach a maximum of about 10 billion in 2100. So the model assumes that the Earth can only hold about 10 billion people. After that, we level off. Is that correct? You could adjust that so that the maximum is 11 billion or 12 billion, depends on what you think. Energy consists of either carbon-based fuels or non-carbon. Technological change takes two forms. There's an economy-wide technological change. Carbon-saving technological change is modeled as reducing the CO2 per unit of output. Carbon fuels are limited in supply. Substitution from carbon to non-carbon fuels takes place over time as carbon-based fuels become more expensive, either because of resource exhaustion or because policies are taken to limit carbon emissions. We can also set a backstop technology price, at which point all production is from renewable. This comes from the hoteling notes prior to spring break. So the DICE model embeds a hoteling model, which assumes that the price of non-renewable resources is going to increase over time as the resources become scarcer. And we're going to transition to cleaner fuels as those become cheaper over time. So that we can even put in a backstop technology, at which point we're going to switch all the way over to other alternative renewable resources. Of course, if we define production, we also have to define how capital evolves. Production uses capital, which is accumulated over time. In the present, capital can be measured as K0. The 0 indicates the initial stock of capital, the stock today, or in the beginning of the model. If capital is KT in period T, then in period T plus 1, or T representing today and T plus 1 representing tomorrow, capital in period T plus 1 is equal to 1 minus delta K, where delta is a depreciation rate. Capital depreciates. It's not infinitely, it doesn't just sit there for an infinite amount of time. Some of it's just going to go bad, essentially. So capital in period T plus 1 is a function of capital in period T times the depreciation rate plus investment. IT is investment. IT describes how investment describes new investment. IT is equal to YT, which is GDP in period T, minus the consumption in period T. And consumption, we have to have some consumption in order to produce more capital and in order to keep our economy running. So whatever we don't consume is invested, and that's translated into new capital. So everything produced but not consumed is invested. You should ask yourself, how does climate change enter a capital evolution? Pausing the video. The answer, through consumption and production. So climate change is entering YT, the GDP in period T. Remember, damages, production in period T, YT, is a function of damages, emissions damages. So of course, YT is going to be affected by climate change. Consumption as well. We're going to consume less as damages increase. We've gone through production. Now let's go to emissions. How does production get translated into emissions? The function for emissions in period T, ET, is sigma T. That first term on the right-hand side of the equal sign is sigma T. This is a conversion factor, or the ratio of uncontrolled industrial emissions to production output. In other words, this is how we're translating production GDP into CO2. Sigma T should be written as CO2 over GDP. If you're in the decarbonization group, this is the parameter that you will be focusing on. You'll be thinking about how we translate GDP or production, the part in red in this equation. So you'll notice that the production function is embedded here. The AT, KT, and LT, that's just the production function. And we're multiplying that by the conversion factor, CO2 per GDP. So AT, KT, and LT are in the units of GDP, and then multiplying that by CO2 per GDP converts this into units of CO2, or emissions. The part we haven't talked about is 1 minus mu t, and which is a function of PC, which is the carbon price. The 1 minus mu t is the emissions control rate. Or in other words, if we imposed a policy in the model or a tax, how would that affect emissions? Obviously, this is going to take the production and limit the emissions that we have from production. Right now, and for the most of what we're doing, this is going to be set to 0. We're not going to impose policies. You should pause the video and ask yourself, what will affect emissions in each period, and what will affect the control rate and carbon intensity, and which can be changed by the user. So what's going to affect emissions in each period? Well, obviously the production, all the things we've talked about in the previous slides, capital level evolution, maybe labor if we make that endogenous, AT, the technological progress, that'll affect emissions in every period. Also, the emissions control rate, or the conversion factor, the carbon CO2 per GDP. That's going to affect emissions in every period. If we think that we're getting cleaner, maybe industrialized countries are getting cleaner, our production in the United States is becoming cleaner. We're producing more electricity, etc., with fewer emissions. But in third world countries, that's not necessarily the case. Africa, the countries within Africa are still, as they evolve, they're going to be producing GDP with a lot more emissions. They're going to use coal probably to produce electricity. Same with China and India. Unless they leapfrog that technology and just start producing electricity with renewable sources and batteries, there's some argument that that's going to happen. But otherwise, there's no reason to believe they wouldn't industrialize in the same manner that we did, the Western countries did, which was by producing a lot of emissions. So the question in the decarbonization group is, how is sigma t going to evolve over time? How is CO2 per GDP going to evolve over time? Is it going to increase, decrease, or remain flat? Basically, all of this can be changed by the user. Anything in this model can be changed by the user. So the previous slide was the flow of emissions, what we're putting into the atmosphere every period. Now we have to talk about the stock of emissions, what exists in the atmosphere regardless of what we're putting in. So the stock of emissions in period t+1, or tomorrow, is equal to the stock of emissions yesterday. The stock of emissions tomorrow is mt+1. The stock of emissions yesterday is mt, multiplied by a depreciation rate, or how much of the emissions are depleted over time. That's going to be 1 minus delta m, whatever leaves the atmosphere, whatever's absorbed by plants and trees, etc., or just leaving the atmosphere into space, or we'll talk about how it's absorbed by the oceans on the next slide. The stock of emissions in t+1 is a function of emissions today, the stock of emissions today, plus the flow of emissions today, ET, plus land use change in forestry. So some of the emissions produced are from land use change in forestry. That's taken as exogenous in the model. How about atmospheric concentrations? Let's take the emissions and translate those into concentrations. So here's the carbon cycle in the model. The carbon cycle consists of 3 reservoirs. The atmosphere, MAT is the atmospheric concentration of carbon in period T. And it's equal to the flow of emissions, industrial and land use change emissions, plus what we had in the atmosphere in the last period, MAT as a function of T-1, plus the carbon concentrations in the upper ocean in the previous period, M up. Then we have upper ocean and biosphere concentrations of CO2 in the current period, which is a function of how much what the concentrations were in the atmosphere in the previous period, what the concentrations were in the upper oceans in the previous period, and what the concentrations were in the lower oceans in the previous period. Then we have lower and deep ocean concentrations, which is a function of the concentrations in the upper oceans in the previous period and the concentrations in the lower oceans in the previous period. So notice that the atmosphere does not mix with the lower oceans directly. It only mixes through the upper oceans. Deep ocean mixing with other reservoirs is extremely slow. That's the phi term. And all these phi terms represent mixing coefficients, or how carbon makes its way through our atmosphere in upper and lower oceans. That was atmospheric concentrations. Now let's go to radiative forcing. Radiative forcing, or climate forcing, is the difference between energy, or sunlight, absorbed by the Earth and energy radiated back to space. So how much energy is the Earth capturing? It's given by the following function. Ft is the forcing, which is a function of eta. It's a forcing parameter, which you can find in the Excel spreadsheet. And the log of the ratio of the atmospheric concentration of CO2 to the current day atmospheric concentration of CO2, MAT, over the pre-industrial CO2 stock. How much have we increased relative to pre-industrial times? Plus the other greenhouse gas emissions, things like methane. These are taken as exogenous. A couple of notes. The forcing parameter is the change in radiative forcing due to greenhouse gases since 1750 from anthropogenic sources. Other greenhouse gases are considered exogenous, so that's what we just said. A higher radiative forcing warms the atmosphere, which then warms the upper oceans and ultimately the lower oceans. That was radiative forcing, which brings us to temperature increases and global climate change. How is temperature modeled? It's done with this equation here. Period T temperature increases with respect to pre-industrial emissions as follows. So temperature in the atmosphere, TAT, at time T, is equal to temperature in the atmosphere in T-1, the previous period, and this is done in years, so that would be last year, plus beta, which is the climate sensitivity parameter. If you're in the climate sensitivity group, then you will be dealing with this parameter here. Climate sensitivity is multiplying the forcing factor, radiative forcing, minus the equilibrium forcing. So why do we have equilibrium forcing? If we stopped polluting right now, the effects of the pollutants, the CO2 in the atmosphere, would not be realized immediately. They'd be realized in now and into the future. So it takes a little while for the climate to respond. It doesn't happen immediately. So we need this equilibrium forcing in here. Climate sensitivity is, we're not certain about it. How sensitive is the climate to different concentrations of CO2? There's different studies that estimate the distribution of this parameter, or the probable distribution of this parameter. It has a fairly fat tail, meaning the right side of the distribution continues on fairly high, while the left side is truncated at 0. Nobody really thinks that there's zero effect of CO2 in the atmosphere on temperatures. The mean of the parameter estimates across the literature is about 3. You'll see that in an Excel file. If we had a climate sensitivity way out to the right-hand side of this graph, then we would have a climate that is very sensitive to changes in CO2. The temperature would probably go up a lot. The IPCC, Intergovernmental Panel on Climate Change, uses these models to try to figure out how the temperatures are going to increase across the globe. There's several model predictions here in this graph. The DICE model, DICE 2007, is that blue line right in the middle. So it's about average as to what we should expect by 2100. So this says about 3 degrees centigrade warming on average by 2100. So that's temperature rise and global climate change. Now let's see how this is translated into damages. Damages are approximated as a quadratic function of temperature. dt is the damages today, which is equal to A0, that's our intercept. In the model that I'm going to give you, A0 is equal to 0, assuming that 0 damages or 0 temperatures are equated with 0 temperature increases are equated with 0 damages. So there's no jump right at a marginal change in temperature. And then we have A1, which is the coefficient on T at time T, temperature at time T. And then A2 is the coefficient on temperature squared at time T. So temperatures directly mapped into damages by these parameters A0, A1, and A2. We also have sea level rise and CO2 fertilization. The basic assumption is that damages from gradual and small climate changes are modest, but that damages rise non-linearly with the extent of climate change. So in other words, the first bit of temperature change we don't really notice it, but as the temperature increases more, this is going to affect us more. That's why we have some curvature. That's why we have T squared in the model, rather than just a linear function of temperature. The estimates also assume that damages are likely to be relatively larger for poor, small, and tropical countries than for rich and large and mid-latitude countries. This comes from regional aggregation. So not in the Excel model, but in the real DICE model, we're estimating damages by region of the globe. The areas that are affected the most are the mid-latitudes or the areas around the equator. The areas affected the least are the higher latitudes. This graph shows how we're estimating the damage function. What's really happening here is we're plotting different damage estimates at different global damage estimates at different temperature changes. So 1 degree change there. We've got a couple of studies that give us the effect of temperature increases on output or GDP in percentage terms. So 1 degree change doesn't have much of an effect. Even some studies show that temperature increases can actually increase output. So that's why we have some negative values here. As we get to higher and higher temperatures, 2.5 degree change and 3 degree change, then the damages are increasing. The percent of output is going down, GDP is declining. So we basically fit a curve to these studies, the damage estimates, a quadratic function to them, and we go with that. So that's translating direct impacts to ecosystems, forests, and crops. Now we place the whole thing into an economic welfare function. Temperature closes the model, feeding back into the damage function. However, in order to distinguish a good situation from a bad one, we need to weigh the costs and benefits of reducing emissions. In other words, we need a welfare function. So our welfare function looks like the equation on the slide here. Welfare is equal to the sum of the utility of consumption in labor. So U is going to be the utility function, which is a function of consumption and labor in any given period. We're summing over all time periods. That's the big sigma. That's a sum here. Summing up over all time periods T in the model. And we're discounting all the utility back to the present period. So rho is a discount rate. It's the pure rate of time preference, or the personal discount rate. We're discounting the utility in every period and summing up those values values to get a welfare function. Utility is just going to be labor. So utilities modeled as labor times consumption over labor raised to 1 minus, I actually don't know the name of that term there. It's the consumption elasticity of marginal utility, or percent change in marginal utility given a percent change in consumption. So this is going to be different for different levels of consumption. What this says is that if you're at a higher level of consumption, the marginal effect of a change in consumption is smaller than if you're at a lower level of consumption. So it's not a linear function. If the damages aren't affecting us all equally. So to give you an example, what this is saying is that if you're in a poor country, if you're in Africa, some country in Africa, the damages are going to affect you more because your level of consumption is lower than if you're in the United States. Your level of consumption to begin with is lower than some industrialized country. And so a marginal change to consumption for somebody in Africa or India is going to be felt more than a marginal change in consumption for somebody in the United States. Maybe we don't get to buy exactly what we want this period in the United States, but that doesn't hurt us as much as somebody who's living paycheck to paycheck or just barely meeting their needs. Changing their consumption a little bit is going to hurt them a lot more. So that's the answer to the question: is what is marginal utility and why does it matter? What is the discount rate and why does it matter? Well, we need to compare current consumption with future consumption. So we have to discount our utility. So that's the welfare function. That's the arrow that takes us from socioeconomic impacts all the way back to production. We're going to maximize that welfare function to figure out over certain parameters to figure out what the emissions path is going to be, what the temperature path is going to be, etc. Question. You should stop this video and ask yourself, how does an integrated assessment model represent a cost-benefit analysis? You should be able to answer this question after listening or reading on the topic. Here's the answer. Integrated assessment models estimate the economic damages associated with climate change. We can incorporate policies into the model, such as a carbon tax, that will affect future emissions and ultimately temperature. That was the mu parameter a while back. These are the policies that translate production into emissions. The model tells us how much the policy reduces climate change damages in dollars and increases costs through carbon prices and emissions abatements. So the model gives us how much we're avoiding, what we're avoiding in damages, but also how much we're going to have to pay, how much we're increasing our costs through carbon prices and emissions abatement. So we're going to balance the avoided damages with the costs of abatement in the model. In summary, sensible policies on global warming should weigh the cost of slowing climate change against the benefits of slower climate change. And integrated assessment models help us do this. Now, when you open the Excel file, you'll see that there are several policy scenarios embedded in the model. The baseline, this is the no emissions control, or the current reality. This is the one we will be working with and adjusting. You can also click through the other tabs and find out how Nordhaus was estimating different policy scenarios. So he has optimal policy, which is emissions and carbon prices to maximize discounted economic welfare. This is the economic optimum according to model assumptions. So in this case, it's figuring out what the carbon prices are or would be to maximize the discounted welfare, or maximize the welfare function. Now this this assumes that we're modeling welfare correctly. We could also model welfare in a different way. The way we have it now, the welfare function I showed you, is treating everyone essentially the same, although we did talk about how the marginal utility is going to be giving more weight to the countries whose consumption is the lowest to begin with. However, we could also think of a welfare function, an alternative welfare function that's minimizing or maximizing the minimum utility. So we're going to find the person or the country with the minimum utility in the world, and we're going to try to maximize that instead. That's another way to think about it. Policy number 3 is limit to 2 degrees Celsius. So here we're going to limit the temperature increase in the model to 2 degrees Celsius and figure out how to get there. Figure out what the optimal or what the necessary tax on emissions would be in order to limit our temperature increases to 2 degrees C. 2 degrees C above pre-industrial levels, 1900. Why 2 degrees C? Well, because above that's where scientists say we are into the uncharted waters, and we don't know what the world would look like after that. Number 4 is strengthen Kyoto Protocol. So this would be modeled on the U.S. proposal in the Kyoto Protocol, which with rich countries beginning at the same time and developing countries joining after 1 to 3 decades. So rich countries reducing their emissions at the beginning of the model and developing countries joining later on. And then we have an ambitious, which was ambitious policy, which was Al Gore's and Stern, who is basically the British equivalent of Al Gore, with early emissions reduction. So this is a little stronger than the Kyoto Protocol. Here are the temperature profiles over time for the different scenarios. You can see under the base case scenario, the blue line in 2007 versus the base case in 2008. The temperatures are going to be increasing fairly linearly for both base case scenarios. This is if we do nothing. You can see how doing nothing for even 1 year is going to affect temperatures over time. Even doing nothing between 2007 and 2008 is going to result in basically a 1 degree temperature gap by 2175. So that should be a little bit of a warning that we should be thinking about what we're doing now. We should not wait. We should be addressing this as soon as possible. The limiting to 2 degrees C, the blue line with the squares, of course, we're imposing that in the model, so the temperature increase is limited to 2 degrees C. The optimum is the green line. That's the social welfare maximizing optimum. We would be by 2175 to about 3.5 degrees C. And the strong Kyoto is the kind of maroonish line with the X's. The concentration profiles that would get us to those temperature increases are as presented in this graph here. The baseline is the pink line with the squares. Obviously, concentration profiles, if we do nothing, are going to just continue to increase. The optimum, we would hit some peak around 2165 and then would start to come down. Concentration profiles, if we kept the temperatures below 2 degrees C, would have to decline over time. And then the strong Kyoto would sort of level off. So now how would we achieve these? So far, it just looks like, well, this is going to be, why don't we just keep it below 2 degrees C or do the optimum? We have to think about how much this is going to cost us. Remember, this is a cost-benefit analysis. We can't just do everything we want to do because it costs us something. Here are carbon prices. The baseline is the pink again. So, of course, if we do nothing, carbon prices are going to be 0. If we look at the optimum, the kind of reddish line here with the diamonds, then that the carbon prices are going to increase smoothly over time and ending about $300 per ton of carbon at 2105. Now, the reason it's difficult to keep temperatures below 2 degrees C is because the carbon prices would have to increase very steeply, as you can see from the green line. By 2075, carbon prices would have to be $1,000 per ton of CO2 or carbon. So this is pretty drastic. What do these carbon prices mean in practice? Okay, so if we had a carbon tax in 2010, dollars per ton of carbon of, let's say, the optimal, let's look at that, of $35 per ton, how much would this affect the price of energy in the US? So gasoline, it would increase gasoline prices by 3.3%. Are you really going to notice this at the pump? Not really, probably. For all energy expenditures, 5.4%. We already talked about how nobody really pays attention to their electricity bills to begin with, and natural gas bills. So a 5.4% increase, probably most people aren't going to notice this. So these carbon prices we're not really going to notice them at fairly low carbon taxes. If we looked at maybe a more ambitious policy like the Gore-Stern policy of a $200 carbon tax, we might see gasoline prices rising by 19%. All right, maybe we would notice that, and that would actually have an effect. We would reduce our gasoline consumption. For all energy expenditures, we would probably, not everyone, but a large portion of people would notice the effect of a 30% increase in their electricity and natural gas bills. Who's going to notice it the most? Probably people with less money. So this is going to hurt the poor disproportionately. These policies are often criticized as being regressive, meaning that they disproportionately hurt the poor. It's also going to impact industries that depend on energy for production, right? So if you produce steel, or you produce even if you're a refinery producing gasoline and jet fuel, you're going to notice this because you rely on electricity to produce your and natural gas to produce your commodity. So we wouldn't just see this in energy expenditures, this increase. We would see this being passed through to the prices of commodities, the prices of goods that we buy on Amazon. So unfortunately, this doesn't tell the whole story. Here's three damage functions from three different models. The model we focused on so far is the DICE model. There's also two different models, one called PAGE and one called FUND. These are three different integrated assessment models that have different assumptions embedded in them, but here are their damage functions. The red is the DICE model damage function, the blue is the PAGE, and the green is the FUND model. What's going on here? Why does the FUND model actually dip below zero at low temperature increases? Well, the FUND model actually shows that at low temperature increases, the global economy benefits. So you see a negative impact on GDP losses, essentially, at low temperatures. This is just zooming in on that. We're showing that the FUND model has a negative GDP loss, so a GDP gain from low temperature increases. What's going on here? Well, certain countries will in fact do better. So imagine you're Russia or Siberia or even Canada, or some latitudes of the US even. As temperatures increase, you're going to be able to grow more crops. The crops that we grow in the Midwest are going to shift northwards up into Canada and up into Russia as temperatures increase. So some countries are going to do better, and this FUND model says that the benefits to the countries that will do better outweighs the cost of the countries that are going to be harmed. Next up, we will estimate the social cost of carbon.